terrorista.
In this video lesson, we're going to look at problem solving with combinations. So first we're going to warm up. We're going to do some questions using a standard deck of cards. So we'll go through them here and maybe try them on your own before I discuss the answers. First question, how many 5-card hands are there from a standard deck of cards? Well, there's 52 cards in a deck, and we have to pick 5. So that's a permutation of 52 cards 5 ways. Except here, order doesn't matter, because a poker hand with 5 cards, whether it's ace, 2, 3, 4, 5, or 2, 3, 4, ace 5, it doesn't matter. So we have to divide those repetitions. And we learned recently that that's actually a combination. That would be a combination of 52 choose 5. So how many 5-card hands have 4 diamonds? In a 52-card deck, there's 4 suits. Each suit has 13 of the same type. So there's 13 diamonds, and we have to pick 4 of them. So it looks like this. That's a combination where we choose from 13 diamonds and grab 4. That leaves us with 39 cards left. 39 and 13 gives 52. So with the 39 cards left, remember we want a 5-card hand, so we have to pick 1. And you multiply those together, you get 27,885. Question C now, if we have to have a 5-card hand with all diamonds, then we have to pick from the 13 diamonds, and it has to be all 5 cards. So it's a combination of 13 choose 5. But there's still a bit to do, and it looks like this. So you 13 choose 5, and from the remaining 39 cards, you choose 0. So you can show it like that, and you'll get 1287. So now, how many 5-card hands are there that have all one suit? Okay, what does that look like? Well, you can have all diamonds, or all hearts, or all spades, or all clubs. So you use combinations. You have each of these 4 cases, and it looks as follows. So from the diamonds, there's 13 of them, and you have to choose 5. Then remaining, there would be 39 non-diamond cards, and you would choose 0. And then the same for all the other cases. All the hearts, 13 choose 5. There would be 39 non-hearts remaining, you'd have to choose 0. This just continues for all the cases. You add those up, you get 5148. We ask how many 5-card hands have exactly 3 kings. Well, in a 52-card deck, 4 of those cards are kings. So we have to choose from 4 kings and grab 3. So we select 3 kings from 4 possible kings. And remember that now there's 48 cards remaining, and we have to select the next 2 cards from those 48 non-kings. And those 2 combinations together give 4512. Important to notice that this 4 and that 48, they add up to the 52 cards that are possible. And then this 3 with that 2 add up to the 5 cards that we're choosing to make a hand. F is very similar kind of approach. So how many 5-card hands have 2 2s, 2 8s, and any other 5th card? You've got a couple combinations here. From the 4 possible 2s, you choose 2 of them. From the 4 possible 8s, you choose 2. And then from the remaining 44 cards, to fill up that 5-card hand, you choose 1. Alright, so thinking back on what we previously looked at and learned in our unit, we saw how the combination formula works. Combination is when you can choose r items from a total of n, and it's especially useful when order is not important. Today we'll look at a couple new concepts that build from the combinations lessons in the previous day, and we'll start building these with an example here. So example 1, how many ways can a committee with at least one member be selected from a board with 6 members on it? Well, if our committee has at least one member, we have all these possibilities. The 1-member committee, 2, 3, all the way to 6-member committee. And for a 1-member committee, it'd be a combination, 6 possibilities, choose 1. The 2-member committee is 6 possibilities, choose 2, and you get 15 combinations. A 3-member committee, and so forth. So for all these 6 possibilities, what you need to do is add up all the combinations. So what you'll end up getting is 6 plus 15 plus 20 plus 15 plus 6 plus 1. You get 63 combinations. I don't know about you, but that seems a little tedious to have to work out every single combination for all the different size committees and then have to add them up. So hopefully you're thinking that there's got to be maybe an easier way to do this. And yeah, there is an easier way to do this. Here's a simple formula. You have to consider the total number of combinations containing at least one item chosen from a group of n distinct items. It's just 2 to the power n minus 1. So let's take a look at another example to show you how this works. In example 2, you've got this artist, there's an apple, an orange, and a pear in his fridge. And we're asked, how many ways can the artist choose one or more pieces of fruit for a still life painting? So in this situation, the artist has 2 choices for each piece. They can either include it or he can leave it out. So 2 choices. We would then say, since the artist has a total of 2 choices, 3 fruits, so 2 times 2 times 2, 8 choices. However, one of these choices, though, is to actually leave out the apple, the orange, and the pear. So the case where you have apple, orange, and pear, you leave that out. Now think back to the original question where it wants 1 or more pieces of fruit. Well, if we're leaving 1 out, that means the following. If the artist wants at least 1 piece of fruit in his painting, he's actually got 2 to the 3 minus 1, which is 8 minus 1, or 7 combinations to choose from. You have to subtract that option where the apple, orange, and pear are all not chosen, so you at least have 1. That's where the formula comes from. 2 to the n minus 1, you get rid of that option where you don't even pick any item. Where here I mean the item to be an apple, a pear, and an orange. So the case where you don't pick an apple, orange, or pear. You get rid of that because of the stipulation that it has to be 1 or more. Let's take a look now at some combinations where we have some identical items. We'll start this with another example here. Example 3. How many ways could we select some cookies from a cookie jar that contains 5 Oreo cookies, 6 Chips Ahoy, and 3 peanut butter cookies? Let's think about what the tree diagram would look like for that, as we know it from previous unit. Okay, so in our first choice, we can have 1, 2, 3, 4, or 5 Oreo cookies. Then we can have up to 6 Chips Ahoy and 3 peanut butter. So we would say 5 times 6 times 3 permutations, and we get 90. What if forgetting to do, or what we're now going to do, is we must take into account that we could actually choose 0 of a certain type of cookie, or even of all the cookies. So you think about, you could choose 1, 2, 3, 4, 5 Oreos, or maybe no Oreos, and that becomes really 6 choices. And the same goes for the Chips Ahoy and for the peanut butter cookies. So you'll end up with the following. There's 6 options here, the original 5 plus 1. There's 7 options here, the original 6 plus 1. And then there are 4 options here, the original 3 plus 1. The extra one's the fact that you chose not to pick that cookie. So really, we have 168 combinations. So if we read the question again, in how many ways could we select some cookies? So we actually have to pick some cookies. When we work this out, we got 168 combinations or possibilities. Here's the problem. One option is no cookies at all, the 0, 0, 0 option, and we don't want that because we need some cookies. So as you can see, we have to select at least one, and we say the following. There's 168 combinations, subtract that combination where you have no cookies at all, and there's really 167 ways to select cookies here. So let's look at a general formula for those kinds of cases. And you have to choose at least one item from groups where you have P of one kind, Q of another, or R of another kind. And dot 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 means maybe you have S, T, U, V, other types. Okay, and you may choose all, some, or none of these items from each group. Then, by the fundamental counting principle, your total number of selections is following. So here's the total selections, and if you at least have to have one item, you have to subtract away that case where you've chosen absolutely no items. That's why we subtract 1. So it's like choosing absolutely no cookies from all 3 choices. And be sure you get this as part of your note. Alright, so example 4 is going to illustrate the last rule we just learned here. So you have 5 rock songs, 2 blues tunes, and 3 jazz pieces. And now, how many ways can you choose songs to make a random playlist? So if you read this question carefully, how many ways can you choose songs to make a random playlist? Well, you actually have to choose some songs. And to choose songs, we have to at least have one song. So from the law we just saw, we have to do the following. You've got 5 rock songs, so you could choose from those 5, or choose none. And you have 2 blues tunes, so you can choose 2, or choose to have none. And same with 3 jazz pieces. Okay? You multiply those 3 together, and those are all your combinations, but you have to subtract the combination where you have picked absolutely no rock songs, blues tunes, and jazz pieces. You end up with 71. Part B now says, what if that playlist must include some jazz? Well, here's how you approach this. So we still have our 5 rock songs plus the 1 choice for not picking a rock song. And we have 2 blues tunes plus the choice of not picking a blues tune. Because it must have jazz, we've got a 3 here. There's 3 jazz pieces to choose from. And we multiply that out and you get 54. And the reason we don't actually subtract 1 from this one is because the stipulation that it must have jazz already guarantees us that we're at least going to have the 1 song to make our random playlist. So in this case, we don't have to subtract 1 because the must gives us a bare minimum of at least a song. It's actually gotta have at least a jazz song. Okay, so more specifically, your 0 to 5 rock songs, 0 to blues songs, 3 jazz, and as I mentioned, because we must have jazz, this will ensure we'll have chosen songs, covers the at least one case, and that's why we don't have to subtract 1 here. Okay, this hopefully isn't that bad, so make sure you're pausing these videos as needed to get caught up on maybe your notes here, or to just refresh any new ideas, because example 5 here is a bit different, and let's just try it, and here we go. Okay, so example 5 reads, how many factors are there for the number 360? What we're going to do is we're going to use what's known as prime factorization for this. To do that, you have to remember that a prime number are the numbers that are only divisible by themselves. So I've listed a bunch here. You can only divide 2 by 2. You can only divide 3 by 3, 5 by 5, etc., etc. 29 only divides by 29. So you get whole numbers. So we're going to make what's called a prime factorization tree. We'll take 360 and we'll write it down. And here's the strategy we're going to take to build this prime factorization tree. We'll start with the original number we were given here, 360, and we'll divide it by any number so we get another whole number. And then we're going to keep repeating this on each number we get until we arrive only at prime numbers, excluding 1. So here we go, 360. I divided by 180, and I got 2. And 2 actually is a prime number, so I'm done with that. I can keep going with 180. I divide that by any number I choose, as long as it's the whole number, and I chose 90. And I chose it smartly, so like I picked 90 because I knew 90 times 2, well, 2 is a prime number, and that's what I'm aiming for. So I get 90 and 2. Keep going. I can keep going with the 90, and I divide that with 30. Again, another smart choice because out comes another prime number, 3. You could have used 45 and 2, same thing, but I chose 30. Keep going with the 30, and I divide that by 15, and I get 2. And I'm going to keep going with that, and I divide by 15 by 3, and I get 5. And you look at the numbers here, and 2, 2, 3, 2, 5, 3, they are only divisible by themselves. They're prime numbers, and you're done with your tree. Okay, so this prime factorization tree has given us some prime numbers. Just to show you, there's 2, 2, 3, number 2, 5, and 3. And those prime numbers, they're the prime factors. You multiply them, 2 times 2 times 3 times 2 times 5 times 3, you get 360. So you've gone and found the prime factors, which multiplied together give 360. But the question asks, how many factors are there for the number 360? So we have to continue, and we do the following. So the total factors use the law we looked at earlier. There's 1, 2, 3 2s. There's 1, 2, 3s, and then there's 1, 5. And you have a choice to make factors of 360. You can work with these numbers. They are factors of 360. And multiply these factors in different ways to come up with the number 360. And it turns out that there's 3 ways to choose the 2s, or not choosing a 2, so that's a 4th way. Then there's 2 ways to choose the 3s, or you don't choose the 3s. And there's 1 way to choose the 5, or you don't choose the 5. So similar to that law from before, you multiply this all together and you get 24 total factors. Keep in mind though, 1's also a factor. 1's a prime number we could add in here. We just don't throw it in there. We remember it for after, as we're doing here. And you have to add that. But we also have to remember we have to subtract 1 as we need at least one factor. That whole idea where if we don't choose any factors, we'll never make 360. So you need to choose at least one, and that's that idea where we have to subtract 1. So the overall result is 24 plus 1 minus 1, and really you end up with 24 total factors that could make the number 360. Kind of different, pretty straightforward. Make your factoring tree, list your factors, count them up, be sure you consider the case where there are none, so you add the 1. Okay, remember that 1's a factor, but then you just have to subtract it out anyways because you at least need some factors. Final answer is just 24 here in this case, and you would then say the number 360 has 24 factors. Okay, so some interesting new ways to look at combinations, and it will only pay off now for you to try these practice questions from your workbook, page 76 through 77, number 1, 8, and 10, 12. Bring your questions to class, and we'll work on these, and look forward to helping you guys out, and all the best.
Do the Harlem Shake.